Okay, we'll go ahead and get started. So, can everyone see my screen and hear me?
Yeah.
Okay, thank you. So today's our last lecture. And then what we'll do today is we'll finish up chapter 10. And then on Wednesday, we'll have an exam which will cover chapters 9 and 10. Then the following Monday, the 7th, is the final exam for the class. And the final exam is a little bit earlier. It's Monday, December 7th at 10:30. So it's a little bit earlier than our normal 11 o'clock start time. Any questions about any of that stuff? Okay. I've posted the answer key to the quiz that you took over the Thanksgiving break. That's posted in Canvas, so you can take a look at that if you'd like. I'm not going to go over it. I think it's pretty self-explanatory, and I should get those quizzes graded either today or tomorrow. So, okay, so the other day we started talking about gases and started going over some of the gas laws. So we're going to continue today with that, and we'll talk about, to start, we'll talk about Charles's law. And what this law tells us is that if we have a fixed amount of gas, so in other words, a constant number of moles of gas at constant pressure, the volume is directly proportional to the absolute temperature. Remember, absolute temperature is the temperature expressed in Kelvin. So if the temperature goes up, the volume goes up. If the temperature goes down, the volume goes down. And that's what this cartoon with the balloons is showing us. So once again, if the temperature expressed in degrees Kelvin of a gas is increased at constant pressure and constant amount of gas, so constant moles, then that volume will increase. And we get a relationship, we can express that relationship as V1 divided by T1 equals V2 divided by T2. And so, as with the previous relationships that we saw regarding gases, we need to make sure that we convert the temperature into Kelvin. So a lot of times it's given in degrees C. If that's the case, then we want to express it in Kelvin before we use the formula and do the calculation. So the V1 and T1 just represent the initial volume and temperature, and then the V2, T2 represent that second volume and temperature. So what this is telling us basically is that as molecules, gas molecules absorb heat, they will occupy a greater volume. So let's take a look at an example of a calculation we could do using Charles' law. So if we had a balloon and it was filled up at a temperature of 25 degrees C and was filled to a volume of 3 liters, what would be its volume if we drop the temperature to minus 15 degrees C? And we're assuming the pressure is constant. So basically think of it as atmospheric pressure. Well, we'd want to identify what our V1 and T1 are. And so those initial conditions, V1 would be 3 liters and T1 would be 25 degrees C. we're trying to determine what that new volume is. So that would be V2. And then that second temperature, T2, would be minus 15C. Remember, in order to use Charles' law, we need to convert our temperatures into Kelvin. So to convert into Kelvin, we add 273 to the degree C value, so that T1 value becomes 298 Kelvin, and that T2 value becomes 258 Kelvin. So now we have our V1 value, we have our two temperature values expressed in Kelvin, and now we can rearrange Charles' law to solve for V2. So if we rearrange that, then we have V2 equals T2 times V1 divided by T1. We can go ahead then and fill in the values for the temperatures and the volume. And we do that, and we get a value of 2.6 liters. So the key things here was deciding which formula we needed to use. In this case, it was Charles' law. And then define which our V1, T1 values were, and then define our V2, T2 values. For the temperatures, we also had to make sure that we converted them from degrees C into Kelvin. If we did all that, then it's a matter of just plugging those values into the variables and then solving, in this case, for that second volume. Well, sometimes we have more than one thing that we're changing. And so in that case, we can combine. In that case, we can combine Boyle's law and Charles's law into what's known as the combined gas law. And we see the combined gas law here, and that tells us that P1 times V1 divided by T1 equals P2 times V2 divided by T2. Let's look at an example of where we would use that combined gas law. So if we had a weather balloon and it was initially inflated to a volume of 53.0 liters, and the pressure was 1 atmosphere, and the temperature was 25 degrees C. Then the balloon goes up in the air, goes to an altitude where the pressure drops to 0.40 atmospheres, and the temperature drops to minus 20 degrees C. Then what would be the volume of the balloon at the final altitude? So this is where we have a couple of things changing. We have temperature changing, we have pressure changing, and we're trying to see what kind of result we'll have for a volume change because of those pressure and temperature changes. So since we're changing more than one of the factors, then we would use the combined gas law, which we just mentioned. So that's the P1 V1 divided by T1 equals P2 V2 divided by T2. And once again, with these gas type calculations, we want to have our temperature in Kelvin. So first thing we're going to do is we're going to convert those two temperatures into Kelvin by adding 273 to the degree C values. So 25 plus 273 gives us 298 for T1. And then minus 20 plus 273 gives us 253 for T2. So now we have P1 values in atmospheres, P2 in atmospheres. We have a volume 1 value in liters. We have our temperatures, both of those in Kelvin, so we're good on our units. And then now we're going to solve for V2. So we can plug those numbers into the combined gas law. We can rearrange to solve for V2. And if we do that, we have P1 times T2 times V1 divided by P2 times T1. we put our values in for our variables, and we get a value of 1.1 times 10 to the second liters. So similar to the last example that we worked, we identified which were our initial values, and then we determined which ones were our second set of values. We then made sure that all of the variables were in the correct units. So in this case, atmospheres for pressure, liters for volume, and Kelvin for temperature. The only one that wasn't in the right units was the temperature variable. So each of those temperature values had to be converted to Kelvin, and we did that by adding 273 to it. Once we got all that straightened up, it was a matter of just plugging those values into the combined gas law, and in this case, solving for volume. When we have gases, they can either be reactive gases or they can be non-reactive gases. If they're non-reactive, then nothing's going on and there's no changes occurring with the gases. But we can have examples, and in this case, we have hydrogen and oxygen, where the gases react and we form a product gas. So in this example, we have hydrogen gas reacting with oxygen gas to form water vapor, water gas. So in this case, just as we had with the solution reactions where some chemical change was taking place, with this, when we combine these, there's also stoichiometry involved. And remember, stoichiometry, we said, was those coefficients in front of the products and reactants, which tell us on a molar basis how much of the molecules react and then how much forms. So similar to regular liquid aqueous type reactions, we can have the same thing with gases. Another thing I want to talk a little bit about is something called Avogadro's law. And this tells us that the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of the gas. And it tells us that at standard temperature and pressure, then 1 mole of any gas occupies 22.4 liters. So mathematically, it tells us that some constant times the number of moles, that equals the volume. So V1 over N1 equals V2 over N2. We have that relationship. If we look at the figure on the right, we see 3 different gases, and there's just a couple things I want to point out here. We have helium, we have nitrogen, and we have methane. We're at standard temperature and pressure, and so our volume is 22.4 liters. So irregardless of which of these gases, they're going to take the same amount of volume up. The other thing I want to point out is that if we look at the formula weights, the molecular weights for each of these compounds, we see for helium it's 4, nitrogen N2 it's 28, methane CH4 it's 16. So the masses are different, but each of those are equal to 1 mole of the gas. Because they're each 1 mole, we see the number of gas molecules are the same. And 6.02 times 10 to the 23rd, hopefully that looks familiar. That's Avogadro's number. And so what it tells us is that in each case, we have 1 mole of gas. So even though the masses are different, the number of gas molecules are the same, because 6.02 times 10 to the 23rd molecules, that's the number of molecules in a mole. So we'll use this relationship of mass and molecules and moles to do some further calculations when we're trying to figure out identities of gases and molecular weights and things like that. So There is some homework associated with this. It's similar to some of the examples we went over. So we're going to move on to the next section unless anyone has any questions on this first section. Okay. So we looked at some simple relationships, which Boyle's law, Charles's law, Avogadro's law, we have the combined gas law. So in all of these gave us relationships between volume and pressure, temperature, number of moles, combinations of these things. So we can, by introducing a proportionality constant, in this case, an ideal gas constant, which we designate as capital R, we can take this information that we've learned so far and write what is known as the ideal gas law or the ideal gas equation. And that's what you see on the bottom here. It's PV equals nRT. So what this tells us is pressure times volume equals the number of moles times this gas constant times the temperature. So we've talked about pressure and volume a little bit. We've talked about moles. We've talked about temperature. We'll talk a little bit now about the gas constant. So the ideal gas constant is what allows us to make this into an actual equation rather than just say something is proportional to it. And so when we write PV equals nRT, just as we said before, we had to make sure our units for temperature were in Kelvin in order to make those previous formulas work. There's different values for that gas constant. And what they depend on is it depends on which units you're using in the gas constant. So if we look here, we see 5 different numerical values for the gas constant. And there some couple of them are the same, but the others are different. And what we see is the key thing is the units column. So we see that each of those constants has a different set of units. So depending upon what the units are in our equation for the other variables, that drives which of these gas constants that we use. For our purposes, we're always going to use the first one. So we're always going to use the one that has a value of 0.08206. And the reason for that is our units, when we fill in pressure, volume, moles, and temperature, our pressure units are always going to be liters, or rather atmospheres. Our volume units are always going to be liters. Moles is going to be moles, and temperature is going to be Kelvin. And because of that, we have to have units canceling out for our dimensional analysis. And so because of that, our gas constant value is going to be this 0.08206 value, because that has the units that we want, that has the proper units. That's the liters, atmosphere, moles, Kelvin. So remember that liters, atmosphere, that's not a subtraction sign, that's just a dash. Same with moles, Kelvin. It's not a subtraction sign, it's just a dash. So liters, atmospheres divided by moles, Kelvin. Those units in that gas constant value are useful to us because it tells us what units our pressure, volume, temperature variables need to be in, because we need to have all these units canceling out. So if our temperature is not in Kelvin, we know we have a problem because our gas constant has Kelvin as part of its unit. Pressure needs to be atmospheres or we have a problem. Volume needs to be liters or we have a problem. So we can use other things, but if we only do that if the units don't match up the way they should. So for our purposes, we're almost always going to use that 0.08206 value for the gas constant. Okay, another thing that we often are interested in knowing is the density of the gas. And remember, we learned earlier that density is mass per volume. Quite often it's expressed as grams per mil. but it's always defined as mass per volume. So we can take the ideal gas equation. Once again, that's the PV equals nRT equation. And we can divide both sides of it by volume and by R times T. If we do that, then we get number of moles divided by volume equals pressure divided by RT. Remember, earlier in the semester, we had talked about how moles times the molecular mass gives us mass. And remember, molecular mass, when we say that, we're talking about the molecular weight of something, molecular weight or atomic weight of something. And so if we take the number of moles times that molecular mass or molecular weight, then our moles cancel, because remember, molecular mass is grams per mole. So the moles would cancel and we'd be left with units of mass. So we're going to leverage that to help us understand how we can get density out of this ideal gas equation. So if we have our rearranged ideal gas equation that we did above, where we had N over V equals P over RT, and we multiply both sides by molecular mass, the capital M, then what we have is we have mass over volume equals that molecular mass, that molecular weight, times the pressure divided by the gas constant times temperature. We said earlier that mass divided by volume, so in this case M over V, that's our definition of density. So we can substitute the symbol for density, D, for M over V, and that tells us that for gases, density equals the molecular mass or molecular weight times the pressure divided by the gas constant times temperature. So by taking that ideal gas equation, PV equals nRT, and doing some manipulations of it, and then remembering that moles times that molecular mass equals mass, and doing some further manipulations of the ideal gas equation, we can get an expression for density. And once again, that expression is D equals M times P, where M is the molecular mass, P is the pressure, and that's divided by RT, where R is the gas constant, and T is the temperature. So what this allows us to do is it allows us to only need to know the molecular mass, the pressure, and the temperature. And if we know those things, then we can calculate the density of a gas. So if we have that molecular weight, we have the pressure, and we have the temperature, we can calculate the density of a gas. If we know the mass of gas that we have, and we know the volume, and we know the temperature, then we can use that information to calculate the molar mass. So in other words, that molecular weight. So by having certain variables defined for us, we can do a calculation and figure out either molar mass or density of a gas. As I mentioned before, if we have a chemical reaction involving gases, that we can write balanced equations just as we do with liquid reactions. And what that tells us is, through the stoichiometry, is how many moles of each reactant we need and how many moles of product are formed. So just like we do for aqueous or liquid-based reactions, we can do that for gas-based reactions. So there's some homework problems associated with this type of stuff. So I'd like to do now is go over a couple of them. So let me pull that up. So 10.37 is the first one. So in 10.37, we're asked to calculate the number of molecules in a deep breath of air whose volume is 2.25 liters at body temperature, which is 37 degrees C, and a pressure of 735 torr. So the first thing we want to do is we want to look and see what information is given to us. So we were given a volume, we're given a temperature, and we're giving a pressure, and we want to find the number of molecules. Well, none of the formulas that we've seen so far have molecules as one of the variables. But remember, we talked a little bit about Avogadro's number, and we said that Avogadro's number tells us that there's 6.02 times 10 to the 23rd molecules in a mole. So we have a relationship that we know between moles and molecules. So what that allows us to do is if we can solve for the number of moles, we have a way to get from moles to molecules. And if we look back at our ideal gas law, we have pressure, great, we have a pressure value. We have volume, we have a volume value. We don't have a number of moles value, but that's related to molecules. So if we can find the number of moles using this formula, then we can convert that eventually to molecules. R is the gas constant, so we're good there. And then finally, T is temperature, so we're given a temperature. So now the issue becomes, okay, if we can solve this equation for the number of moles involved, then we can use Avogadro's number to switch that to molecules. But the first thing we need to do is set up our variables in the PV equals nRT equation. And we need to make sure that we have the right units. And this is where our constant is going to help. Remember, we said the constant that we'll be using will be the 0.08206 liters atmospheres divided by moles Kelvin. So that tells us a few things there, the units on that constant. It tells us that the volume needs to be in liters. So we look and we see our volume was given to us as 2.25 liters. So we're in good shape there, that's in liters. Then our pressure needs to be in atmospheres. Well, the pressure that we were given is in torr, 735 torr. So that's not going to work in terms of our dimensional analysis of canceling out units. So what we'll have to do is we'll have to convert the pressure, 735 torrs, into atmospheres. We know that our conversion for atmospheres and torrs is 1 atmosphere equals 760 torr. So by dividing that 735 torr by 760, we are able to cancel our torr units, and now our units are an atmosphere. We go ahead and do that calculation, and we now see that 735 torr equals 0.967 atmospheres. So that's good. Our volume's in the right units, liters. Our pressure now is in the correct unit in atmospheres. So now what do we have left? We have moles, which is trying to solve. We have our gas constant, that's good. Last one we need to look at is temperature. Temperature was given to us as 37 degrees C. We know that that needs to be switched to Kelvin because our gas constant has a mole Kelvin in the denominator. So we need to switch this to Kelvin to be compatible with that Kelvin unit in the gas constant. And so we take our 37 degrees C and add 273 to it to convert to Kelvin, and that gives us 310 Kelvin. So now all of our variables are in the correct units. So we can go ahead and we can plug in those numbers into our PV equals nRT equation. So we'll have 0.967 atmospheres times 2.25 liters equals the number of moles, which is what we're trying to solve for, times that gas constant of 0.08206, and then times the 310 Kelvin. So if we go ahead and put those numbers in and then solve for N, we get a value of 0.0855 moles. But remember, we're not done yet because the question asked us how many molecules were in a deep breath. So we have a mole value, 0.0855 moles, and we know from Avogadro's number that we learned early on in the semester that there are 6.02 times 10 to the 23rd molecules in a mole. So if we multiply that Avogadro's number value times the moles value, we see the moles in the denominator of that Avogadro's number conversion cancel with the moles of what we just calculated. And now we have units of molecules. And that value we get is 5.15 times 10 to the 22nd molecules. So just to go back and kind of recap, what we had to do is we had to make a decision on what formula we were going to use. We were given pressure, volume, temperature. We basically were trying to find molecules which we can relate to moles. That led us to our ideal gas law, and that equation being PV equals nRT. Then it was a matter of looking at our gas constant, 0.08206, and looking at the units of that, which are liters atmosphere divided by moles Kelvin, and seeing what units the pressure, the volume, and the temperature needed to be in to work with this particular version of the gas constant. So our pressure needed to be in atmospheres. It was given to us in torr. So we had to do a conversion there of the pressure from torr into atmosphere. The volume we were okay because we wanted it in liters, and that's how it was given to us. And then temperature, we needed that to be in Kelvin because of, once again, of the gas constant we were using. And since that was given to us in degrees C, we had to add the 273 to it to convert from degrees C to Kelvin. So once we had all that set up, we had everything in the right units, then we could plug it into the ideal gas law and solve for that, giving us a number of moles. We remembered back how we can relate moles to molecules, and that was our Avogadro's number that we had talked about early in the semester. And that's the 6.02 times 10 to the 23rd molecules in a mole. So there's that many molecules in any mole of anything. Remember, we saw that when we looked at those three different gases. And so even though they were different gases, they all had the same amount of molecules in them because it was a mole of each of those gases. So we used that information, that conversion, to convert the moles into a molecule value. So a few things we had to do there, a few things we had to remember, but one of the keys is using dimensional analysis and using the units that are in that gas constant to tell us what units we needed to get our variables changed into. Okay, let's look at part B of this question. So in part B, we're told the adult blue whale has a lung capacity of 5 times 10 to the 3rd liters. Calculate the mass of air contained in an adult blue whale's lungs at 0 degrees C and 1 atmosphere. And we're assuming that the air behaves ideally. So if it behaves ideally, that means we can use the ideal gas law. The other piece of information we're given in the question is assume an average molar mass, in other words, molecular weight, of 28.98 grams per mole. So once again, we have, let's take a look at our variables that we're given. So we're trying to fill in the blanks, so to speak, in our PV equals nRT formula. So we're given a volume of 5 times 10 to the third liters. Those units are good because our gas constant works in units of liters, so our liters units are good. Pressure is 1 atmosphere. Okay, that's good as well because our pressure units for this gas constant are atmosphere, so we're good there. And then temperature is 0 degrees C. Well, we know that needs to be switched to Kelvin because our units for the gas constant and temperature units are Kelvin. So let's go ahead and convert that 0 degrees C to 273 Kelvin. That's an easy one because 0 plus 273 is 273. So now we have a volume in liters, a pressure in atmospheres, and a temperature in Kelvin. So we have all the right units that we wanted to be able to then plug these values in to our PV equals nRT formula. So we go ahead and do that. We have 1 atmosphere times 5 times 10 to the third liters equals some number of moles, which is what we're trying to calculate. And then times our gas constant, which is 0.08206 times 273 Kelvin as our temperature. If we go ahead and solve for the number of moles, we see that that is equal to 223 moles. Well, we want to get into mass, which means we want to get into grams. And we know that to convert from moles to grams, or vice versa, we need to leverage that molar mass, that molecular weight. And we were given that information in the problem. We were told that the molar mass, the average molar mass, is 28.98 grams per mole. So if we have 223 moles, if we multiply that by 28.98 grams per mole, we see that the moles units will cancel through our dimensional analysis, and we'll be left with units of grams. And then our final value is 6.46 times 10 to the third grams. Okay, any questions about either of those two questions that we just worked on? All right, let's move on to 10.51 and go through that one. So in 10.51, we're asked to calculate the density of NO2 gas, and we're told that it's at 0.970 atmospheres and 35 degrees C. So here we need to remember that when we're talking density, we're usually talking grams per mil, although it can be grams per liter, but essentially we're talking weight per volume. And we had discussed how you can rearrange things going from moles and using molar masses and weights and things like that, masses, to convert amongst those. So we know that our ideal gas law, PV equals nRT, will give us a mole value. We also know what the gas is that we're working with. It's NO2. So we can calculate a molar mass for NO2. 1 nitrogen atom, 2 oxygen atoms, so 1 times 14 plus 2 times 16. That tells us the molar mass of NO2 is 46. So now we know the molar mass. We can solve for moles. So we'll be able to use that information to get a mass value through the ideal gas law equation. Once we have a mass value, then it's just a question of a matter of ratioing that mass to a volume, and then mass per volume, as I said before, that's our definition of density. So then we'll be okay. We'll be able to calculate this density for NO2. So let's take a look once again at what we have. We have an atmospheres value for pressure, so we're good there. we have a degree C value for temperature. We know we need to get that into Kelvin, so we'll add 273 to 35 to get 308 Kelvin. And then now we can go over to our PV equals nRT. We're going to rearrange it so that we have moles divided by volume, because eventually we're going to want mass per volume. But for right now in our equation, we can get a value that is expressed as moles per volume, because that will lead us to a density type value, a mass per volume density value. So P, as we said, was 0.970 atmospheres divided by the rate constant, 0.08206 liters, atmospheres, moles, Kelvin, and then divided by 308 Kelvin for our temperature. We can start doing our dimensional analysis. And what that tells us is, if we do the dimensional analysis, the answer to this math is going to be in units of moles per liter, because the atmospheres cancel out and the Kelvin units cancel out, leaving us with just moles per liter. So we get a value of 0.0384 moles per liter. Now it's a matter of just converting the moles to a mass value. And we said before that we do that by using the molar mass. We'd calculated that up above. That's the molecular weight, where 1 times 14 for the nitrogen contribution, plus 2 times 16 for the oxygen contribution, for a total of 46. So 46 grams per mole. Dimensional analysis tells us that the grams goes in the numerator, the mole goes in the denominator. So then that allows us to cancel the units of moles out. Now we're left with units of grams. If we want to have grams per mil, we need to change that liter, 1 liter, into mils. And we know that 1,000 milliliters equals 1 liter. So if we do that, then we get a value of 1.77 times 10 to the minus 3 grams per mil. If we wanted to leave it in grams per liter, which we could, because that's a mass per volume unit, then it would just be 1.77 times 1.77 grams per liter. So once again, going over kind of the thinking in this problem, we were looking for a density value. We know that the definition of density is mass per volume. We also know that in the ideal gas law, we can do calculations where we have moles involved. If we can get to moles and we know what gas we're working with, we can use the molar mass to convert that into grams using that molecular weight of the gas. And we can have volume also in this relationship, in this equation. And so we can have a mass per volume, which is our definition of density. So we make sure everything is in the correct units, and those units are driven off of that gas constant units that we're using. And so by using the correct units in our variables to make sure things are canceling out on the units that are associated with the gas constant we're using, that allows us to know that we have things set up properly. Then once we get to moles, then we know that we can use that molar mass value to convert it into a gram value. So understanding ideal gas law, understanding the units we need to be in, understanding and remembering that relationship between moles, grams, molecular weight, molecules, Avogadro's number, all that stuff, it all ties together. We learned it quite a while ago, but it's still something that we're going to be holding on to and using. So kind of combining all of that allows us, in this case, to solve for a density. Okay, any questions about how we did that problem? Okay, let's move on to the next section. So we talked a little bit about how if gases are reactive, we can know how they react in terms of the coefficients, the stoichiometry associated with the reaction that we would have. A lot of times gases don't react. And so, but yet they can be combined in a container. And when they don't react and they're combined, they really behave as if they were alone in the container. And so if you have a mixture of gases that don't react, the total pressure of that mixture is the sum of the individual pressures of the gases. So in other words, if you had 3 gases, gas 1, 2, and 3, you could calculate out the individual pressures for each of those gases. And then to get the gas total for the 3 when you combine them would just be the sum of those 3 individual pressures. And this leads us to something called mole fraction. So because if gases aren't reactive gases, they pretty much behave as if they're alone. You can relate that amount of each one in terms of partial pressures. And so what we have here is an explanation of that using the ideal gas law. So in the numerator, we have P1 equals N1 times RT divided by V. And that just signifies the 1 subscript signify this is gas number 1. Then in the denominator, we have PT equals NT times RT divided by V. In this case, the T subscript is representative of the total pressure and the total number of moles. You see that RT and V, so gas constant, of course, doesn't change, it's a constant, but temperature and volume, those don't have a subscript. They don't have a subscript because we're not changing the temperature, we're not changing the volume. We're just putting some number of individual gases into the same container at the same temperature, and then we're trying to figure out information about that. So those don't change. So if we go ahead and look at these relationships, we see that we can cancel out RT divided by V from the numerator and the denominator, and we're left with just P1 over PT equals N1 over NT. And remember, small n, those are the number of moles of the gas, 1 divided by the number of moles of all the gases totaled up. So what we see is that these pressure ratios hold up essentially the same as the molar ratios. And that ratio of the moles of one of the gases, number of moles of one of the gases to the total number of moles of gas, that's called the mole fraction. So this N1 over NT is known as the mole fraction. What this allows us to do is we look at this, we rearrange this equation. So remember here, we had P1 over P2 equals N1 over NT. We can rearrange that and we can say the pressure for an individual gas is equal to the mole ratio times the total pressure. So in other words, the number of moles of the gas we're interested in divided by the number of total moles of gas times that total pressure, that is equal to the individual pressure of a particular gas in that mix. So if we talk a little bit about kinetic molecular theory, we know that the gas laws that we've talked about kind of tell us what happens under certain conditions. So let's talk, so we kind of have looked at the math behind it a little bit, but let's talk about why that is, kind of the theory behind it. So gases consist of large number of molecules, and these molecules are always moving around. So they're not staying still, they're moving around, and the motion is random. We typically say that the combined volume of all the molecules of the gas is negligible compared to the total volume in which the gas is contained. So in other words, if you have a container and you've put some different gases in there, we say that the molecules associated with the gas, the actual molecule volume, is pretty small compared to the size of the container. And so these molecules are running around in the container, but that volume that they take up is pretty small compared to the volume of the container. We also say because of this, that any attractive and repulsive forces between the gas molecules, that's pretty small as well. And when we're talking about this theory, we usually don't worry about that. So the reason for that, once again, is these things are moving around. And so if they were to come into contact or come close to each other, you could have interaction, either attraction or repulsion. But because there's so much space between them, that doesn't happen very often. If it does happen, then you'll get some energy transfer between the molecules because of the collisions. But the average kinetic energy, so in other words, if you average it over time, it doesn't change. And that's assuming that you've kept the temperature constant. If you increase the temperature, then you're going to increase things. But if you keep the temperature constant, we're saying over time it really doesn't change. And that's because you don't get a lot of these occurring. And then finally, that average kinetic energy of the molecules, it's proportional to the absolute temperature. So as you might imagine, you increase the temperature, the kinetic energy value goes up, you decrease it, it goes down. So it is proportional to the temperature. When we talk about molecules moving around, you'll see expressed as average speed, molecular speed, and you'll hear root mean square speed. And root mean square speed is associated with the average kinetic energy. These values are usually pretty close to each other. So for our purposes, we're not going to worry about the root mean squared speed. We're going to focus on the average speed of the molecules. And if we look at these two figures up at the top of the page, there's a couple things I want to point out. One is on the one on the right, where they do have the average speed and the root mean square value of the speed. We see that those, as I was saying, those values are pretty close to each other. There's not a big difference. The other thing I want to point out is on the left-hand plot, the blue plot is the molecular speed at 0 degrees C, and then the red plot is at 100 degrees C. And what you notice is, as you increase that temperature from 0 degrees C to 100 degrees C, we see a shift in the apex of the plot. So the peak of the plot for each of those, we see it shift as we go from 0 degrees C to 100 degrees C. What this is telling us is just reinforcing what we talked about a few moments ago, is that as you increase the temperature, that molecular speed increases. So here's another plot that is useful for us. So if we look at this plot, we see several different molecules plotted with looking at the apex of the plots. We see the apex shifting to the right, and as you shift to the right, you're increasing the molecular speed. And we see that H2 has the highest molecular speed and O2 has the lowest. What we see from this is that if we were to sit down and calculate the molecular mass, the molecular weight of each of these, we would see that H2 has the smallest molecular weight. So that's 2, right? 1 for each of the hydrogen atoms. And then oxygen would be 32, because 2 times 16 is 32. So that has the highest molecular weight of them. And what this relationship tells us is that the lower the mass, the greater the speed. And the heavier the molecule, the slower the speed. And that's what this plot is telling us. There's the math equation for it, that root mean square value is equal to the square root of 3 RT divided by M. And that's all fine. You can plug numbers in and do some calculations with that. But what it's really telling us is the smaller that molecule's mass is, okay, the lower the molecular weight of the molecule, the faster it's going to be. And the plot, I think, does a nice job of illustrating that. Said before, as we increase the volume at a constant temperature. So if we have an increase in volume at constant temperature, it causes the pressure to decrease. And that's because if we increase that volume, we're going to have fewer collisions with the walls. So remember, pressure is based on collisions with the walls. It's based on collisions with other molecules. And so if we do something that changes the number of collisions, in this case, we didn't change the temperature. All we did was increase the volume. Well, then there's going to be less of those collisions. And so that's going to result in the pressure decreasing. If we increase the temperature, but keep the volume constant, then the pressure is going to go up. And that's because we're going to get more collisions with the walls. We could also get more collisions with the other molecules. But you increase that temperature, you haven't changed the volume, so the container's the same and stuff's moving faster. And so now you're going to get more collisions. That leads to higher pressure. So for the gases, the pressures center around, are you increasing or decreasing the collisions of the gas molecules? If you're increasing the collisions, then the pressure goes up. If you're decreasing the collisions, the pressure goes down. So there's a couple things that are similar, but their definitions are slightly different. So let's go through that, and they're called effusion and diffusion. So effusion is defined as the escape of a gas molecule through a tiny hole into an evacuated space. So in this picture that we see a bunch of gas molecules in a container. At the bottom of the container, midway through the container, there's a small hole poked into the bottom part there. And then below it is another section of the container that's been evacuated. So in other words, they've taken all the air out and everything. So there's nothing in there. And the gas molecules from the top want to go through that pinhole and down into the empty area. This ability for the gas molecules to go through that small hole is limited because the gas molecules are randomly shooting all around, and they're running into each other, possibly they're running into the walls, all that. So it has to hit at exactly the right spot in order to be able to go through that pinhole. So this process of getting everything lined up perfectly so that it goes through that hole, that's effusion. The other one, diffusion, is when you have a space and it's one open space and you introduce a gas into it. It could be one gas, two gases, whatever, it doesn't matter, but you introduce a gas into it And then the gas is going to randomly start to roam around, and it'll spread throughout the whole space. Remember, we talked about earlier that gases like to spread out, and they won't just stay in one corner or something like that. They spread out to take over the whole space, no matter how big it is. So it takes time for that to happen, and that's what diffusion is. It's this randomness kind of going out and spreading out into space. So slight difference in what's going on in these two processes, effusion and diffusion. Like I said, effusion has to do with a gas hitting a particular target to get through, in this case, a pinhole. Diffusion is just a more broad term of going throughout the whole area and the gas moving about to where it's throughout the whole space. Something called Graham's law describes diffusion and effusion. And what it does is it relates molar masses of two gases to their rate of speed of traveling around. And as you might expect, lighter gas has a faster rate of speed. So lighter gas would be defined as ones with lower molecular mass. And we had that plot a little while ago that showed that the smaller the molar mass, the faster the gas was. And that's what this supports. So as we said, lighter gas moves at a faster rate. The one caveat to that is if you do have some molecular collisions, that makes things a little more complicated. Diffusion rate of gases is slower than the molecular speed. So those are slightly different things, and that's because of the collisions. And because of collisions, you do get some collisions, you have the direction of motion of a gas molecule is always changing. And then finally, the average distance traveled by a molecule between collisions is defined as the mean free path, and that's going to vary with pressure. And the way to think of this is if you're walking through a crowd, you walk for a certain amount of space or a certain amount of time without running into anyone, but at some point you're going to bump into someone, and then it's going to kind of slow you down a little, and then you're going to maybe have to shift your bounce a little bit to one side or the other, and then it varies your path a little bit. So that distance you would walk without running into someone, that'd be your mean free path. So, we've spent a lot of time talking about ideal gases and how they behave. And that's what we typically focus on, especially in this class. I do just want to make a few comments about in reality, gases don't always behave ideally, and that gases only conform to that ideal gas equation at relatively high temperatures and low pressure. And the reason for that is some of the assumptions that we make when we talk about ideal gas, aren't exactly correct. And so we make an assumption that gases have negligible volume, that those gas molecules don't take up any space. Well, that's not totally correct. And we make the assumption that there's no attractive forces between gas molecules. Or repulsion forces, and that's not really true either. So even though they don't take up much space, they do take up some space. Even though there's not a lot of interaction, there is some, and because of that, the ideal gas law doesn't take that into account, and because of that, it doesn't always hold up when you get into the real world. In order to make some corrections for this non-ideal behavior that can occur, you can actually make some adjustments to the ideal gas law. And one of these is known as the van der Waals equation. And so we'll take a look at that a little bit. So here we see, instead of it being PV equals nRT, it's P times this N squared A over V squared times V minus NB equals nRT. So let's take a look at what we're talking about on these corrections. So we have a slight correction to our pressure term, and we have a correction to our volume term. And so if we look at that correction to the pressure term, N, of course, is number of moles. A is a value that tells us how strongly gas molecules are attracted to each other. V, of course, is volume. Then the correction to the volume term, N once again is number of moles, and B is a measure of the volume occupied by the gas molecules. So in other words, we're adding a little bit to the pressure term, and that's based on that attraction that the gas molecules might have for each other. And we're taking a little bit off the volume term because we want to compensate for what the volume of the gas molecules might be. So as you might expect, larger molecules have larger volumes and tend to have greater intermolecular attractive forces. So larger molecules, this has a bigger impact than smaller molecules. And on the table, we see some of these van der Waals constants for some different gas molecules. And so you would use those values and plug them into that equation to do a correction to that ideal gas law. We're not going to worry about that much. For the most part for us, the ideal gas law will work fine, but I did just want to mention this. Now, as one last thing, I'd like to just do one calculation and walk you through that to make sure everyone understands how to do this. So let's take a look at problem 10.63. In this problem, we're told we have a mixture containing 0.765 moles of helium gas, 0.330 moles of neon gas, and 0.110 moles of argon gas. And we're told that it's in a 10-liter container and the temperature is 25 degrees C. And we want to calculate what's the partial pressure of each of these gases. And then we want to calculate what the total pressure is of the gases of this mixture. So we go back and we use our ideal gas law, PV equals nRT, and we look and see, we're trying to calculate pressure, so we don't know what that is. We have a volume. The volume doesn't change for any of the gases. For all of them, it's 10 liters. Liters is the units we want, so that's good. Number of moles, we're given a different number of moles for each of those, so we'll use that information. We have our ideal gas law constant. We'll once again use the 0.08206 value. And then finally, we have a temperature value. We're told the temperature is 25 degrees C. By now, hopefully, we know we need to convert the degrees C value into a Kelvin value. And so we do that and we get 298. So we add that 273 to it and we get 298 Kelvin as our temperature. So now we remember that these are non-reactive gases, and for non-reactive gases, our total pressure is the sum of each of the individual pressures of the gases. So let's go ahead and calculate out what these partial pressures are for the individual ones, and then we can add them up and get a total pressure for the mixture. So the helium contribution will be that pressure times 10 liters, and we have that equal to 0.765 moles for helium, then times our gas constant, and then times the temperature. We go ahead and solve for that pressure, and we get a value of 1.87 atmospheres for helium. We do a similar calculation for neon using that 0.330 mole value, and for argon using the 0.110 mole value for argon. We do those calculations and we get values of 0.807 atmospheres for neon and 0.269 atmospheres for argon. So here we have our three individual pressures for helium, neon, and argon. And we said for these non-reactive gases, to get the total pressure of the mixture, then we would just add up these 3 partial pressures from the 3 individual gases. And we add those up and we get a value of 2.95 atmospheres. So that is it for today's lecture. Does anyone have any questions on what we went over? Okay, then just let me repeat again that this Wednesday we'll have exam number 5, and that will cover chapters 9 and 10. It'll be in Canvas, so go in into Canvas and take that exam, please. And then next Monday, December 7th, it starts a little bit earlier. It starts at 10:30. You'll have the final exam for the class Monday, December 7th at 10:30. So once again, that'll be in Canvas, so go online and take that exam. As I said earlier also, I posted the answers to quiz number 5. That was the take-home quiz you just completed. And then I'll hopefully get those graded in the next day or 2. So in the meantime, thanks for being in class this semester, and in between now and these exams, if you have any questions or anything, just send me an email. If no one has any questions, then that'll be it for today. Thank you.
Thank you.
Thank you.